Artificial intelligence of things empowers sensing nodes with real-time data acquisition, intelligent analytics, and autonomous decision-making capabilities. AIoT systems typically consist of a massive number of nodes that are widely distributed and require continuous wireless communication and data uploading. The resulting communication energy overhead is substantial, imposing stringent energy constraints on the long-term autonomous operation of the nodes. To extend the operating lifetime of the nodes, energy and sensing signals can be simultaneously extracted from ambient vibrations to build self-powered sensing nodes. Self-powered sensing systems typically integrate an energy harvester, a self-sensing transducer, and intelligent algorithms. Signals generated by the harvester can serve both as an energy flow to power the entire system and as sensing outputs that reflect environmental conditions and node states. By combining these with ultra-low power intelligent algorithms, AIoT sensing nodes can achieve long-term self-sustained operation. Vibration energy harvesters are based on three mechanisms: piezoelectric, electromagnetic, and triboelectric, each suited to different vibration scenarios. Piezoelectric vibration energy harvesters are well suited for medium to high frequency vibrations. They offer high electromagnetic conversion efficiency and high power density. With linear or nonlinear structural designs, effective energy harvesting can be achieved across different bandwidth requirements. Electromagnetic vibration energy harvesters are suitable for low to medium frequency vibration environments. They typically feature low output impedance and strong load driving capability. With nonlinear structural designs, they can also harvest energy under random and complex operating conditions. Triboelectric nanogenerators realize charge transfer and electrical output through four fundamental working nodes. They exhibit strong energy harvesting capability under low-frequency, large-amplitude motions. While delivering energy, an energy harvester's electrical output can also be directly used as sensing information in different scenarios, enabling self-sensing at the node level. In industrial applications, self-powered sensors provide a practical solution for long-term, wireless and low-maintenance monitoring of unattended or power-constrained edge equipment, enabling large-scale deployment and sustained operation without external power supplies. Self-sensing technologies can further empower environmental modelling by enabling the passive detection of signals such as vibration, wind and waves. They also offer a sustainable self-powered monitoring approach for wearable and biomedical applications. From control panels to smart gloves and exoskeletons, self-powered sensing technologies are driving human-machine interaction beyond button-based inputs toward natural interfaces that are multimodal, real-time and continuous, enabling lighter, lower power and long-lasting human-machine collaboration. For self-powered sensing nodes, intelligence depends not only on the algorithms themselves, but also, critically, on where the computer is deployed. Cloud, edge, and on-device computing correspond to distinct power budgets and engineering trade-offs. Cloud computing plays a central role in AIoT as a hub for computation and storage. It frees the node from local hardware limitations and provides strong flexibility and scalability. Edge computing pushes part of the model down to edge nodes, where pre-processing or feature extraction is performed locally. Only compact, refined data are then uploaded to the cloud, which can significantly reduce the energy cost of wireless transmission. On-device computing further moves intelligence entirely onto the device, transmitting final results only when necessary. In some cases, the system can operate in a long-term silent mode. This strategy minimizes transmission energy and allocates limited energy more efficiently to local computation and continuous monitoring. Looking ahead, AIoT is expected to advance through hybrid energy management, cooperative energy harvesting, and event-driven near-sensor processing, ultimately enabling a fully integrated, self-powered architecture that unifies energy, sensing, and computing. Such co-designed systems are poised to become a key foundation for next-generation AIoT, supporting robust monitoring and intelligent decision-making in complex, dynamic environments.